Welcome to our quantum deep dive. Today, we're plunging really deep into the world of subatomic particles. We're looking for one that, well, might just be hiding from us.
Yeah, and we're using a really insightful essay by Jörg Schneepath as our guide. It's called Stop Quark, ein Schlüsselteilchen der Quantenphysik. It really lays out why this hypothetical particle is potentially so important. Okay, well, let's try and unpack this then. What exactly is this stop quark? And, why spend so much time and energy looking for it if we're not even sure it exists?
Well, that's the fascinating part, isn't it? Stop quark isn't something we've directly seen.
Right.
But it's a key piece, maybe the key piece, in a theoretical idea called supersymmetry, or SUSY for short. You can sort of think of it as a partner particle, specifically to the top quark, which we do know exists.
A partner. Okay, the essay talks about this SUSY idea. Is it like for every matter particle, there's a force particle partner and vice versa? That's the core concept, yeah. The top quark is a fermion, a matter particle. It has this property called spin, which is 12 for the top. Its proposed partner, the stop quark, would actually be a different kind of particle, a scalar boson. Spin zero.
Spin zero. Okay, so same family, but different fundamental property.
Exactly.
The essay says they'd have the same electric charge, plus 23. But what about mass? That seems important.
Mass. Well, that's the million-dollar question, isn't it? Or maybe trillion electron volt question. We know the top quark is heavy, really heavy, around 173 GeVia. But the stop quark's mass, the theory doesn't pin it down nearly as well. It's variable. Could be quite a range.
Which makes finding it harder, I guess. Or explains why we haven't yet.
Precisely. And that leads us right into why it's considered such a key particle. The essay really dives into how it could solve some, fundamental problems with our current best theory, the standard model.
Right. This is where it gets really interesting, like the hierarchy problem. What's that all about?
Okay, yeah, the hierarchy problem. This is probably its biggest selling point, theoretically speaking. It's this puzzle surrounding the mass of the Higgs boson. We found the Higgs, right? Its mass is about 125 GeV.
Mm-hmm. Seems specific.
It is, but when you calculate how quantum effects, especially from particles like the top quark interacting with it, should affect its mass, well, the calculations suggest it should be huge, like orders and orders of magnitude larger. Way up near the Planck scale, maybe 1019 G, unless something stabilizes it.
Wow. So the theory predicts a giant mass, but we measure a tiny one. The essay mentioned quantum corrections and top quark loops.
Exactly those. They effectively add an enormous theoretical weight. To get the 125 DV we see, you'd need some kind of massive cancellation. It requires this incredibly precise, almost unnatural fine-tuning of parameters, like balancing a needle on its point across the universe. It just feels wrong to many physicists.
Feels like we're missing something. So how does the stop quark fix this apparent unnaturalness?
Well, this is the elegant part of SUSY. If the stop quark exists, it also contributes these quantum corrections to the Higgs mass. But crucially, because it's a different type of particle, a boson partner to a fermion, its contribution comes with the opposite mathematical sign.
So it subtracts instead of adds. A negative correction.
Exactly. So the essay explains if the stop quark exists, and importantly, if its mass isn't too heavy, maybe in the few hundred GeV to a few TeV range, not ridiculously far from the Higgs or top masses, then its negative correction can naturally cancel out a large part of the positive correction from the top quark.
Making the Higgs mass stable and, naturally small without that crazy fine-tuning.
Precisely. That's the naturalness problem that SUSY, and specifically the stop quark, is proposed to solve. It makes the Higgs mass make sense.
Okay, that's a big one. But the essay also links it to dark matter. How does that work?
Right. It's another potential bonus. Many SUSY models predict that the lightest of all the new supersymmetric particles, often something called a neutralino, would be stable, and it would be electrically neutral, interact very weakly. Sounds familiar.
Sounds like the properties we think dark matter has.
Exactly. So this lightest supersymmetric particle, the LSP, is a prime candidate for dark matter. And the stop quark could potentially decay into standard particles plus this neutralino. So it provides a production mechanism.
Interesting. And there was also something about unifying forces.
Yeah, that's another hint the essay mentions. If you look at how the strengths of the fundamental forces, strong, weak, electromagnetic, change with energy, in the standard model they get close at high energies but don't quite meet. Add in the effects of all the SUSY particles, and calculations show these strengths can converge beautifully at a very high energy scale. It suggests a deeper unification.
Okay, so theoretically it's very appealing. Solves the Higgs mass problem, gives us dark matter, helps unify forces. But the big question, Have we seen it? The essay talks about CERN, the LHC.
Right. The Large Hadron Collider at CERN is ground zero for the search. That's where the experiments ATLAS and CMS smash protons together at incredible energies. The hope is that in those collisions, you might produce stop quarks, if they exist, and aren't too heavy.
And then you look for the debris. What kind of signs, what signatures are they looking for? The essay described some decay paths.
The main channel they often look for is the stop quark decaying into a top quark, and that neutralino, the potential dark matter particle.
The invisible one, right?
Yes, exactly. And that invisibility is key to the signature. The neutralino just flies out of the detector without interacting. So that the detectors see is a top quark, which we know how to identify, plus nothing where there should be momentum balance. It looks like energy is missing.
Missing transverse energy. Because something invisible carried it away.
Precisely. The essay also mentions other possibilities, like decay to a bottom quark and a charged Higgs partner, depending on the exact masses and details of the specific USY model.
But it sounds like finding it is really hard. The essay mentioned challenges.
Oh, absolutely. It's a huge challenge. First, there's the mass issue we talked about. If the stop quark is just too heavy, heavier than, say, 1.5 TeV or so, the LHC might not have enough energy to produce it frequently enough to see it clearly.
We might just not be hitting hard enough yet.
Could be. And then there's the background problem.
Background, you mean other stuff happening in the collisions?
Yeah, perfectly normal, standard model processes. Things like producing pairs of top quarks or producing W and Z bosons along with jets of other particles. These everyday events can sometimes look surprisingly similar to the expected signature of a stop quark decay.
So you have to sift through tons of noise to find a maybe signal.
Exactly. It requires incredibly sophisticated analysis, machine learning, really pushing the limits of data science to try and pick out a potential stop signal from this overwhelming background.
Okay, so, as of today, no confirmed sighting. Which brings us to the essay's critical question. Why haven't we found it?
Yeah. The essay lays out the possibilities pretty clearly. 1, maybe it is just too heavy for the current LHC. We need more energy or more data. 2, maybe its decays are more complicated than the simplest models predict. Maybe it decays in ways we haven't focused on as much, or maybe it lives for a short time before decaying, creating an exotic signature.
Like those R-hadrons or steponium things mentioned.
Right, those are more complex scenarios. Or possibility 3.
Or maybe CSY isn't the answer. At least not this simple version with a relatively light SUT. Stop solving the hierarchy problem.
That's the elephant in the room, really. The essay raises that fundamental question. If the stop quark isn't found where naturalness suggests it should be, maybe supersymmetry isn't realized in nature like we thought. Or maybe it's realized in a very different, less natural way.
Which means we need alternatives. The essay listed some.
Exactly. If SUSY isn't the path forward for solving the hierarchy problem, physicists are exploring other ideas. Things like composite Higgs models, the idea that the Higgs isn't fundamental but made of smaller stuff. Or theories with extra dimensions. Maybe gravity behaves differently because there are hidden spatial dimensions we don't see.
Like the Randall-Sundrum theory mentioned.
Yeah, that's one example. And also things like Higgs portal dark matter, where dark matter talks to us mainly via the Higgs. These are all different attempts to explain the puzzles, the Higgs mass, dark matter without relying on supersymmetry, and the stop quark.
And the essay makes the point that experiments are key to figuring out which path, if any, is right.
Absolutely. Theory can propose many ideas, but at the end of the day, data decides.
Now here's a twist I wasn't expecting. The essay connects this hunt for a fundamental particle to quantum technologies. How on earth does that work?
Yeah, it's not immediately obvious, is it? You're not building quantum computers out of stop quarks, that's for sure. But the research itself, the sheer complexity of the theory, the massive data challenges, pushes technology in directions that overlap with quantum tech.
Okay, like the data analysis, needing better ways to sift through all that background noise we talked about.
Precisely. The essay notes that searching for these incredibly rare signals in petabytes of LHC data is a massive computational problem. Machine learning is already crucial, and there's active research into whether quantum machine learning algorithms could, in the future, provide an advantage in finding these needles in the haystack.
And simulating the theories themselves.
That's another potential link. Quantum field theories, especially complex ones like SUSY, are notoriously hard to simulate accurately on classical computers. The essay suggests that quantum computers might be a natural fit for tackling these kinds of simulations eventually, helping us understand the theory better or improving related calculations like lattice QCD.
And it even mentions some more abstract links between SUSY concepts and quantum information.
Yeah, that was pretty speculative, but interesting. The idea that the fundamental symmetry between bosons and fermions in SUY might have some kind of mathematical analogy to quantum entanglement. Or maybe that the structure of SUSY could offer insights into building states that are robust against errors, like in quantum error correction. It's more conceptual, that connection.
Still fascinating. And then there are the spin-offs from just building the detectors, right?
Definitely. The essay highlights that. Developing the incredibly sensitive, fast detectors needed for the LHC has led to advances used in medical imaging, like PET scanners, or in materials science for developing new quantum sensors. Plus, just handling the fire hose of data from the LHC has driven innovations in high-performance computing and networking, which are relevant across science, including for developing quantum computing infrastructure.
Wow. Okay, so this one hypothetical particle really casts a long shadow. It touches the Higgs, dark matter, force unification, and it connects, indirectly at least, to future tech. That's quite a portfolio, all from this one essay's focus.
It really does underscore how interconnected physics is, doesn't it? The essay sums it up nicely. The stop quark is sort of the poster child for supersymmetry's potential solutions to big problems like the hierarchy problem and dark matter.
But the fact that we haven't found it yet puts us at a really interesting point. It makes you question, is it just heavier? Are the decays weird? Or is the whole CUSY picture not quite right?
Exactly that. We're at a crossroads. The essay points to what's next. The high luminosity upgrade to the LHC will give us way more data, maybe enough to see a faint signal or push the mass limits much higher. And then there are proposals for even bigger machines, like a future circular collider that could reach higher energies still.
Or, if those searches also come up empty for the natural stop quark, it really forces the community to double down on those alternative theories, right? Composite Higgs, extra dimensions.
Precisely. The essay concludes that this search, win or lose, discovery or exclusion, is absolutely crucial. Finding the stop quark would confirm SUSY and revolutionize particle physics. Not finding it, especially where naturalness suggests it should be, forces us to confront the possibility that nature uses different principles, maybe even more profound ones, to structure reality and keep the Higgs mass stable. And that really leaves us with a big question to chew on, doesn't it? If this elegant solution, the stop quark solving the hierarchy problem naturally, just isn't there, what else could be going on? What fundamental principle are we missing that prevents the universe from being balanced on this theoretical knife edge?
That is definitely something to mull over. This deep dive into the stop quark has certainly highlighted how many huge questions are still wide open. And our guide through this was that really excellent essay by Jorgo Schneepat. He gave us a great roadmap for understanding this complex topic. So a big thank you for joining us on this deep dive. We hope it gave you some food for thought, maybe sparked some new questions. Goodbye for now.